Section 4.2, Subspaces. A subset W of vector space V is called a subspace of V if W is itself a vector space under the addition and scalar multiplication defined on V. In order to see if subsets in general of vector spaces are subspaces, we have a subspace test, because not every subset of a vector space is automatically going to be a subspace. So to test if they are, we see that if W is a set of one or more vectors in a vector space V, then W is a subspace of V if and only if we have these two conditions satisfied. So we need U and V to be vectors in W, for their sum to be also in W, and we need that if K is a scalar and U is a vector in W, then KU is in W. So we need the sum of any two vectors to be in W, and we need their scalar multiple to be in W. So notice just these two conditions is enough to show that something's a subspace, as opposed to having to go and show all 10 axioms. So this is a much more concise way of showing that something is a vector space, provided that we already know that it's a subset of another vector space. To prove that the subspace test is all we need, notice that if W is a subspace of V, then all of the vector space axioms hold in W, including 1 and 6. So that means if W is a subspace, then of course these are going to be true. So that means that we have that half of our theorem is true. We just have to do the converse now. So in the other direction, because remember this is if and only if, so both directions have to work. So in the other direction, assume that conditions A and B hold. Let's check and make sure that this thing's a subspace. Notice these are axioms 1 and 6. Since axioms 2, 3, 7, 8, 9, and 10 are inherited from V, if all of those are true in V, then they'll be true in W. We just have to check that axioms 4 and 5 hold in W. So for this purpose, we let U be any vector in W. Then from condition B, we must have that KU is a vector in W for every scalar. So that means if we take 0 times U, then we'll get the 0 vector. If we take minus 1 times U, we'll get the negative vector of U. So that gives us axioms 4 and 5, and that means we have all 10 axioms just from these two conditions. So as an example, how about we take a look at V being any vector space, and we'll show that the subset W equals the 0 vector of V, consisting of the 0 vector only, is a subspace of V called the 0 subspace of V. So we just have to check if the sum of any two vectors in W is a vector in W, but notice 0 plus 0 is equal to the 0 vector. And now we'll check the scalar multiple, but any scalar times 0 is 0, so both of those are in W. So that means that W is in fact a subspace of V by the subspace test. V by the subspace test. Okay, for our next example, how about we show that the lines through the origin are subspaces of R2 and of R3. So I'm just going to do it for R3, then it should be obvious that the same argument will work for R2. Do a proof by picture, if you will. So here's R3, and then here's a line W, subset of R3. Notice if I draw any vector U on that line and any other vector V, then their sum, well, I'll just take vector V and I'll stick it the tail of V onto the tip of U. So it looks something like this. That'll be U plus V. And that's obviously on the line W, any sum will be. So we just have to check for scalar multiples. So I'll draw R3 again. And I'll draw W again. And notice this will be true for the same reason. I'll just take some arbitrary vector U and I'll scalar multiply it by some scalar K. And that'll either be in this direction or the other direction. Doesn't really matter. Either way, it'll still be on W. So W is closed under scalar multiplication and addition, so W is a subspace. we can similarly show that planes through the origin are subspaces of R3. So I'll try drawing this now. How about I draw the plane W first? I'll draw the axis behind it. Okay, so that's my y-axis. So that's my plane W. Now here's vector u. And let's say here's an arbitrary vector v. So I can get their sum with the parallelogram rule. Here's u plus v. Notice that u plus v is still in w. And notice also I can scale u. So that would be ku, also still in w. So again, proof by picture. Let W be the set of points xy in R2 for which x is greater than or equal to 0 and y is greater than or equal to 0. Let's show that this set is not a subspace of R2. So how about I try drawing this? This will be our first non-example of a subspace. So let's say here is W. It's this entire shaded part of the upper half plane. It's like the first quadrant. So I'll call that W. Let's say I have some vector in here. How about 1, 1? Then notice if I scale that by -1, then I get -1, -1 vector, which is not in W. So more concretely, if we have v equals 1, 1, that's in W, and -1 v is -1, -1, not in W. So therefore, W is not closed. Under scalar multiplication. So it's a subset, but not a subspace. How about we show that the set of symmetric n by n matrices is a subspace of M and n, the set of n by n matrices. So you might remember that we did theorem 1.7.2, which told us that sums and scalar multiples of n by n symmetric matrices are symmetric. Okay, so that means that the set of symmetric n by n matrices is in fact a subspace of the set of n by n matrices M and n by the subspace test. By the way, there are a whole bunch of other subspaces of M and n, including the upper triangular matrices, lower triangular matrices, diagonal matrices, lots of different subspaces. We just happen to only do the symmetric ones. How about we show that the set of invertible n by n matrices is not a subspace of M and n. So we'll just take a vector u. In this case, that's a matrix. That's, for example, we'll do 2 by 2. You can generalize this if you want. So I'll do it for 1, 2, 2, 5. And I'll take another vector v. That'll be -1, -2, 2, 5. And notice if I take 0 times u, then that's 0, 0, 0, 0. And its determinant is 0, so it is not invertible. Since it's not invertible, it's not in this subset, so that means that the subset doesn't have a 0 vector. Notice also, if we take the sum of those vectors, we get 0, 4, 0, 10, which also has a determinant of 0, 10 times 0 minus 4 times 0, so it's also not invertible. So this subset is not closed under scalar multiplication or under addition, so it's super not a subspace. Let's next show that the set of continuous functions on -infinity, infinity, denoted by c minus infinity, infinity, is a subspace of f minus infinity, infinity, the set of functions in general. So first remember that a sum of continuous functions is continuous. But we also have that a constant times a continuous function is continuous. Multiplying constants by continuous functions doesn't make them not continuous anymore. So there you go, that's enough for the subspace test. That means that c minus infinity, infinity is a subspace of f minus infinity, infinity by the subspace test. Okay, how about we show that the set of functions with m continuous derivatives on -infinity, infinity, and the set of functions with derivatives of all orders -infinity, infinity are subspaces of f minus infinity, infinity, denoted by cm minus infinity, infinity, and c infinity, minus infinity, infinity, respectively. So a same thing as before, basically a sum of functions with m continuous derivatives on -infinity, infinity still will have m continuous derivatives. And a constant times a function with m continuous derivatives on -infinity, infinity still has m continuous derivatives. This is the same for functions with derivatives of all orders for c infinity. So again, just apply the subspace test. I won't even write it. Okay, how about we show the set of all polynomials is a subspace of f minus infinity, infinity. We'll denote that by p infinity. So let's come up with two arbitrary polynomials. How about p of x equals a0 plus a1x plus and so on through an xn, and we can let another polynomial be q of x, so that'll be z0 b1 of x b1 times x plus, and so on to bn xn. Let's add these two guys. We get px plus qx is equal to a0 plus b0 plus a1 plus b1 times x, and so on, till you get to an plus bn times xn. So that's definitely a polynomial still. Then we look at a constant times polynomial, and that'll be ka0 plus ka1x, and so on. So yeah, this is still a polynomial too. Oops, I forgot the constant in the last term. Okay, so again, subspace test says that's a subspace. Closed under addition, scalar multiplication. How about we show that the set of polynomials of positive degree n is not a subspace of f minus infinity infinity, but that for each non-negative integer n, the polynomials of degree n or less form a subspace, denoted by Pn. So again, let's take some polynomials. However, to show, when we want to show something is not a subspace, we only have to find one particular vector doesn't work. Like before when we found that vector 1, 1, where we scaled it and got -1, that wasn't in the set. So in this case, let's come up with a vector that's going to break everything. So a polynomial that'll work is 1 plus 2x plus 3x squared. So that's in P2. And let's come up with qx. That'll be 5 plus 7x minus 3x squared. That's also in P2. And notice if I take p of x plus q of x, then that'll be 6 plus 9x, and that's in P1. So if we only look at polynomials with the exact degree 2 and try to add those together, we could still come up with polynomials that'll have a lower degree, like 1, because we get some cancellation. So as a result, in order to make this thing a subspace, we have to include all of the lower degree polynomials also. So we need to make sure that we have the degree n or less in order to get a subspace. If we only consider the degree n, it will not be a subspace because we just won't have enough polynomials in there to make sure that we're closed under addition. Notice I didn't exactly show it for all of Pn in generality, but I think the example is good enough to convince you maybe. Let's now determine whether the indicated set of matrices is a subspace of M22. So now first we have the set U consisting of all matrices of the form x0, 2xy. So how about we look at a general matrix A, and let's make, instead of xy, I'll just use, let's say, A and B. So I'll take A, 0, 2A, B. I'm using different letters so that I can also come up with a matrix B in U. So I have a second vector that I can play with. So I'll make this one C0, 2C, D. Could have also just made one x1 and y1 and one x2, y2, but this is fine. So let's look at A plus B. Let's see if it's closed under addition. So we have A plus C, 2 times A plus C, 0, and B plus D. Okay, but notice that's the same thing as making A plus C equal to x. Then the bottom is still 2x. We still have a 0 here, and we still have some other character here, y, some other entry. So how about scalar multiplication? Let's see if it's closed under that. So we'll take k times a, then we'll get 2ka, we'll get 0, k times 0 is still 0, and kb. And again, still of that form. So both of these guys are in U. So that means yes, U is a subspace of M22. Okay, how about this next set, W, consisting of all 2 by 2 matrices A, such that A times 1, 2 is equal to 1 minus 1. So we'll take A equals 1, 0, minus 1, 0, and we've got A 1, 2 is equal to 1, 0, minus 1, 0, times 1, 2, and that's equal to 1 minus 1. Okay, so my A worked so far, because that means that A is in fact in W, because multiplying by 1, 2 gave me something where I get 1 minus 1. Let's look at a scalar multiple of it though. Let's say 2A. So that's going to multiply by 1, 2, and I'll get 2 times A is 2, 0, minus 2, 0, and multiply by 1, 2, and I get 2 minus 2, which is a problem because it doesn't equal 1 minus 1. So this means that even though A was in W, 2A is not in W. So W is not closed under scalar multiplication. This wasn't the only possible A that would have broken this, but you know, sometimes it can be a little bit tricky to come up with candidates, and this one seemed pretty simple. Notice this fails subspace test because it's not closed under scalar multiplications. W is not a subspace of M22. Next, how about we determine whether the indicated set of polynomials is a subspace of P2. First, let's do the set U consisting of all polynomials of the form P equals 1 plus AX minus AX squared, where A is a real number. So how about we look at the polynomial P equals 1 plus X minus X squared. Notice that's in U. It's a polynomial form 1 plus AX minus AX squared. And let's look at Q, where Q is equal to 1 plus 2X minus 2X squared, also in U. Then notice P plus Q is equal to 2 plus 3X minus 3X squared. And that 2 is definitely not of the form 1 plus x minus x squared, so that's not in U. So U is not closed under addition, so U is not a subspace of P2. And remember, to show it wasn't a subspace, we just had to find any two polynomials whose sum wouldn't be in there, or any scalar multiple of a polynomial that wouldn't be in there. Okay, how about next the set W consisting of all polynomials P and P2 such that P of 2 is equal to 0. Notice in this case, no matter what P and Q we use, when we look at the sum P plus Q and evaluate that at 2, then we're going to get P of 2 plus Q of 2, which is equal to 0 plus 0, which is 0. So that's going to be in W. And similarly, if I look at the scalar multiple of any vector P in this set, then that's going to be K times P of 2. I guess it's a little presumptuous of me to say that look at this vector because I haven't shown it's a subspace yet, but it is because K times P of 2 is just K times 0, which is 0. So W is a subspace of P2 by the subspace test. If W1, W2 through WR are subspaces of a vector space V, then the intersection of these subspaces is also a subspace of V. To prove this, let W be the intersection of the subspaces. This set is not empty because each of these subspaces contains the zero vector. Remember that the set of 0, even though it looks like it has nothing in it, it actually has 0 inside of it. That's an element, so it's not empty. So their intersection must also have the zero vector if all of these subspaces have the zero vector. So we just have to show that W is closed under addition and scalar multiplication. To prove closure under addition, let's let U and V be vectors in W. Since W is the intersection of all of the W1, W2 through WRs, it follows that U and V also lie in each of these subspaces. Moreover, since these subspaces are closed under addition and scalar multiplication, they also all contain the vectors U plus V and KU for every scalar K, and hence so does their intersection W. Next theorem is that the solution set of a homogeneous linear system AX equals 0 of M equations in n unknowns is a subspace of Rn. To prove this, how about we let W be the solution set of the system. The set W is not empty because it contains at least the trivial solution x equals 0. To show that W is a subspace of Rn, we must show that it is closed under addition and scalar multiplication by our subspace test. To do this, let's let x1 and x2 be vectors in W. Since these vectors are solutions of Ax equals 0, remember, any vector in W is a solution of Ax equals 0, we must have Ax1 equals 0 and Ax2 equals 0. So then, from these equations and the distributive property, it must be that A times x1 plus x2 is A times x1 plus x2 is 0 plus 0, which is 0. So W is closed under addition. Similarly, if K is any scalar, then A times kx1, well, we could just pull out the K. So we get K times AX1, which is K times 0, because AX1 is 0, so W is also closed under scalar multiplication. In each part of the solution of the linear systems provided, let's give a geometric description of the solution set. Starting with the first one, notice that this is a scalar multiple of this. So pretty clearly we can write everything in terms of the top line. So in other words, y and z will end up being free variables. So we could just parameterize them. We could write x equals, moving this to the other side, 2y, 3z, or 2s minus 3t, where y equals s and z equals t. It's not super important though. How we get the solution is more important to interpret the solution, which we can do by rewriting x in terms of y and z. So x equals 2y minus 3z, so that we can write x minus 2y plus 3z equals 0. Because in this form, it becomes obvious that geometrically this is a plane through the origin with the normal vector n equals 1, minus 2, 3. For the second one, notice that in this case this is a scalar multiple of this, so z is going to be your free variable. Shouldn't be super surprising if you solve it to see that x is minus 5t, y is minus t, and c is t. You should recognize that as a line through the origin. Because those are the parametric equations of line through the origin. That is parallel to the vector v with coefficients as its coordinates. So minus 5, minus 1, 1. Then we've got this guy, which could be reduced to the identity through matrix operations. You could rewrite this as 1, 0, 0, and still equals 0, 0, 1, oops, 0, 1, 0, 0, 0, 1. In other words, x equals 0, y equals 0, and z equals 0. Because this entire thing times x, y, z equals 0, 0, 0. So that means that this subspace is just the 0 vector. Geometrically, that's just the point, the origin. Last one, this says 0 times x equals 0. In other words, 0 equals 0. And same thing for y and z. But it doesn't matter what you make x, y, and z in this case then, because any value, when you multiply it by 0, will still give you 0. So all real values of x, y, z work. In other words, our solution space is all of R3. Let's end by mentioning this last theorem. If A is an n by n matrix, then the kernel of the matrix transformation Ta from Rn to Rm, the set of vectors in Rn that Ta maps into the 0 vector in Rm, is a subspace of Rn. So all of the vectors that the transformation sends to 0, when you put them all together, that's called the kernel, and it turns out that that's a subspace of Rn.